Okay guys, in this video we're going to be talking about the kinetic molecular theory, which is a microscopic model for gases, which can be used to understand the gas laws. In the kinetic molecular theory, we talk about molecules of gas moving around randomly, that is, they're moving in different directions, and they have different speeds. There's a distribution of speeds. Some molecules are moving fast, some molecules are moving slow. The kinetic molecular theory is based on a couple of assumptions. First, that the gas molecules have a very small size compared to the volume in which they are moving. So gas molecules have negligible volume. Another assumption is that gas molecules do not interact with one another. So there's no forces of attraction or repulsion between different gas molecules, and also they don't interact with the walls of their container. Another assumption is that the distribution of velocities and speeds is isotropic, which means that it is uniform, or it's not uniform, it's even in all directions. That is, there's no preferred direction for the molecules to travel in. Generally speaking, the molecules will travel in a straight line until they collide with a wall, or if they collide with another molecule, they just bounce off one another. And then will continue traveling in a straight line. The collisions between molecules and the walls of the container are assumed to be elastic, which means that when the molecule strikes a container, it doesn't lose any energy, right? It bounces off the walls of the container, it bounces off other molecules, and has the same energy that it had before. So there's no energy loss associated with collisions. And then the last assumption of kinetic molecular theory is that the average kinetic energy of the molecules within the gas sample is proportional to the temperature of the sample. And so down below I have an equation that we're not really going to use that much. And we've seen it before in the thermochemistry chapter, that the kinetic energy of an object is 1/2 the mass of the object times its speed squared. In this case, we're talking about a lot of molecules that are moving around, and they all have different speeds. And so what we're saying is that the average molecule within that sample, it has a kinetic energy that's proportional to the temperature. So the higher the temperature of the gas sample, the faster the molecules are moving on average, the more kinetic energy they have on average. So that's what this relationship says here. So high temperature means fast-moving molecules, low temperature means slower-moving molecules on average. We don't have to worry about, deriving the ideal gas equation, but I just wanted to point out that from the kinetic theory of gases, you can actually derive the ideal gas equation of state. You can derive the ideal gas law. And along the way, we'll just bring up a couple of important concepts that you should be aware of. Okay, so first of all, where does gas pressure come from? Why does a gas exert a pressure on the walls of the container? Well, it's because the gas molecules are colliding with the walls of their container. So it's these collisions between the molecules and the container walls that gives rise to a force which is related to the pressure that the gas exerts. And so here's a way of thinking about this pressure. The pressure that the gas exerts should be proportional to the frequency of collisions with the wall. So how often per second does a gas molecule strike the wall of a container? And then how hard does the molecule strike the wall? So what's the average force of a collision between a gas molecule and the container that holds it in? Well, the collision frequency, which is represented by a capital Z, is going to be proportional to the average speed of the molecules. So molecules that are moving faster will collide with the wall more frequently. That makes sense. And then the other factor here, the number density, this refers to the number of molecules per unit volume. The higher the number density, the more collisions you would expect with the wall of the container. So these are the two main factors that affect the collision frequency. It's the average speed and then the number density of the sample. Here I've written this as moles per volume. So the other factor that affects the pressure is how hard do these molecules strike the walls of the container. Well, the average force is going to be related to a quantity from physics called the momentum. And the momentum, on average, of a gas molecule is going to be the mass of that molecule times the average speed. So again, we see that the average speed plays a role in determining the pressure. So if we combine these two factors, if we combine the collision frequency with the average force of the collision, and we work through the math, we get that this pressure is going to be proportional to the number density times the mass times the speed squared. Well, if you close your eyes and think back to this slide here, we see that we've recovered the mass times the speed squared. So we have everything we need to make the kinetic energy. Okay, and so the pressure is related to the average kinetic energy of the gas molecules times the number density. We can replace that average kinetic energy with the temperature. And now what do we see? Pressure is proportional to number of moles times temperature divided by volume. The proportionality factor is the molar gas constant. Okay, so using the ideas of kinetic molecular theory, trying to understand how gases move, and treating them using these simple assumptions, you can actually derive the ideal gas law. And then you can use the model itself to understand the empirical gas laws that we've looked at previously. For example, Gay-Lussac's law, or Hamilton's law. Pressure is proportional to temperature. Okay, so the molecules in the container, they have some, initial temperature, and that corresponds to some average kinetic energy, which determines the pressure. But then if you heat up the gas sample, so you raise the temperature, that's going to cause the molecules to start moving faster. Okay, and they're going to collide with the wall more frequently, and they're going to collide with the wall harder on average when they do. And so that's going to give rise to an increase in the pressure. Okay, so you can use these kinetic theory ideas to understand all of the empirical gas laws that we've looked at so far. I'll leave it to you to look at the other ones. We'll move on here to this conceptual question here. So let's consider a sealed glass bottle of helium at room temperature. If we immerse that bottle in an ice bath, so we cool it down, how will this affect the pressure of the gas? Will it decrease, increase, or will there be no change? Well, we already know from Gay-Lussac's law that if you cool down a gas at constant volume, the pressure is going to go down. So we know that the pressure is going to go down. What is the best explanation of this? So we want to choose from statements A through E. What's the best reason for explaining why the pressure goes down? Statement A. The force of the collisions of the molecules with the walls increases with increasing temperature. Well, does that really make sense? Would that cause the pressure to go down? If the molecules are hitting the wall harder, would the pressure go down? No, the pressure would go up. So A is a false statement. The atoms have significantly greater volumes at low temperature. Well, that doesn't make sense either. Atoms have, they do have a size to them, but, for a gas, most of the gas consists of empty space, and so the gas molecules' volume is essentially negligible. So it's not B. That one doesn't make sense either. Statement C. The frequency and force of molecular collisions with the wall decreases, which is going to, that decreases with decreasing temperature. That's right on the money. C is the correct answer. That's the one that we want. Let's just rule out parts D and E. The average kinetic energy of the atoms remains constant with decreasing temperature. That's false. The average kinetic energy is directly proportional to temperature. So if you decrease the temperature, the molecules are going to move more slowly on average. They're going to have a smaller kinetic energy. Will not remain the same. The concentration of gas decreases, resulting in a decrease in the collision frequency of the walls with the walls of the container. That's false. The number density will not be impacted by the temperature if volume and number of moles is constant. So E is a false statement as well. Let's take a look at what's next. Explain Charles' law and Dalton's law in terms of kinetic theory. Well, for Charles' law, if you increase the temperature of the molecules while keeping the pressure fixed, you need to somehow reduce the number density of the gas sample in order to keep the average, to keep the pressure the same. And so in order to, if we look back at the equation here, in order to keep the collision frequency the same, you would need a larger volume if you increase the temperature. So when you increase the temperature, that's going to cause the speeds to go up, which would tend to make the pressure increase. In order to keep the pressure constant, you would have to make the volume larger. You'd have to compensate for the increase in average speed by making the volume larger, which would then reduce the collision frequency. So that's how you would explain Charles' law. The best way to explain Dalton's law, that the total pressure of an ideal gas mixture is just a sum of the partial pressures, where each gas is treated independently like an ideal gas, is to note the assumption that in the kinetic molecular theory, the gas molecules for an ideal gas, they don't interact with one another. Okay, so you might have a mixture of helium and argon, but because the gas molecules are so far apart in the gas, it's mostly empty space, they don't feel one another. There's no interaction between them. There's no attraction or repulsion between them. And so, it makes no difference that there's another gas there. So the gases behave independently, and as a consequence of that, the total pressure is simply just a sum of all of the partial pressures for the individual gas components. This slide goes into a little bit more depth regarding the distribution of molecular speeds. So as I mentioned before, we treat gas molecules as if they're moving randomly. And what we mean by that is that the molecules are moving in different directions. Okay, so they have randomized directions. And they also have randomized speeds. So some molecules are moving fast, some molecules are moving slow. This curve that I'm showing here, the number of molecules that have a particular speed, is called the distribution of molecular speeds. And so you see that there are very few molecules that have zero speed, right? Almost none of them have zero speed. And then you see that the distribution of speeds peaks, and so there's this speed right here. This is the most probable speed, right? So you have a lot of molecules that are moving, a little bit less than 400 meters per second. And then over here, this is where the average speed would be. Notice how the distribution kind of tails off. So you're going to have more molecules, at these higher speeds, and so this is where the average of the distribution would be. And then as you go to very high speeds, you find fewer and fewer molecules that have these very high speeds. So this is what we mean by a distribution of speeds, the number of molecules that have a particular speed. And this is at a given temperature. Okay? If you change the temperature, it's going to change this distribution, and I think we'll look at that on one of the upcoming slides. Let's see, I've already talked about the most probable speed and the root mean square speed, so this is basically the average speed. And then this is just showing the relationship between the average kinetic energy and the average and the root mean square speed squared. So this is kinetic energy is 1/2 times the mass, the molar mass of the gas, times the root mean squares speed squared. And what it's doing is it's showing you that there's a relationship between, like where this relationship comes from here. So the root mean square speed is related to the temperature through this equation. You see that as the temperature increases, the average speed is going to increase. As you increase the molar mass, the average speed is going to decrease. So there's two important factors over here in the root mean square speed, the temperature and the molar mass. The higher the temperature, the higher the average speed. The higher the molar mass, the smaller the root mean square speed. And these two diagrams illustrate that process explicitly. So take a look at the set of curves over here for nitrogen. So this is the distribution of speeds at different temperatures. You see that as you increase the temperature for the nitrogen gas, what happens is the average speed increases. So nitrogen molecules at 1,000 degrees Kelvin are moving a lot faster than nitrogen molecules at 100 degrees Kelvin. Right? The average speed is much larger. Moreover, you see that the distribution broadens as well. So not only does the average speed shift to higher speeds as you increase the temperature, the breadth of the distribution also gets larger as you go to higher temperatures. This set of curves over here investigates the shift in the distribution with respect to molar mass. So these are all at the same temperature. So let's say it's all at 300 degrees Kelvin. Comparing xenon to helium, you see that the heavier xenon atoms, they have a much lower average speed compared to the helium, and the distribution is much narrower compared to helium. So as you increase the molar mass, what you find is that the distribution shifts to smaller and smaller average speeds, and you find that the distribution of speeds gets narrower and narrower. Okay, so these are the two important trends with respect to the distribution of gas speeds. There's one for temperature and one for molar mass, and it would be useful to keep them straight. Here what we're going to do is a couple of illustrative calculations. We're going to illustrate calculating the root mean square speed for oxygen at 21 degrees Celsius and 15.7 atmospheres pressure. The root mean square speed is given by the square root of 3RT over the molar mass. Okay, and so we want to put, for this, we want to put everything in SI units. Okay, so notice that I've got the gas constant here expressed in joules rather than liter atmospheres. So we're going to take 3 times 8.314 joules per mole Kelvin. We want the temperature in Kelvin. So 21 degrees is 294 Kelvin. And then when we do the molar mass, we're going to want that in kilograms as well. And so we need to take that to be 32.00 times 10 to the minus 3 kilograms per mole. So that's the molar mass in kilograms per mole, not in grams per mole. We need that in order to get the units to work out. If I've done that correctly, we're getting 479 meters per second. Just to give you a reference, how fast is that? That's about the speed of a bullet. Okay, gas molecules at room temperature are traveling as fast as a typical bullet would travel. The follow-up problem, part B, is identical. There's nothing that needs to be done. You just need to change the molar mass for carbon tetrachloride, and you need to change the temperature, but it's calculated in exactly the same way, and I have a feeling you're going to get comparable to that. It'll be several hundred meters per second. Here, this next problem is a little trickier, okay? It's worded kind of funny, so that's one thing that makes it hard. But once we understand it, it's not too bad. At what temperature do hydrogen molecules have the same root mean square speed as nitrogen molecules at 455 degrees Celsius? So what you need to do is to calculate the root mean square speed for nitrogen. You need to find that. Okay, so that's the square root of 3RT over M. So we'll take 3 times 8.314 joules per mole Kelvin. 455 is 728 Kelvin. Divide that by 28.02 times 10 to the minus 3 kilograms per mole. So we'll get that speed. So I'm getting 805 meters per second. Okay, so that's the speed of the nitrogen. Now they want to know at what temperature will the root mean square speed of hydrogen equal 805. So they give us the speed, and then we need to find the value of temperature, which makes this the speed. So we'll take we'll rearrange the equation. So we need to take the 805. We'll say that the temperature is the 805 meters per second squared. And then we need to multiply by the molar mass of hydrogen and divide by 3R rather. So we'll plug in those numbers. Hydrogen 2.02 times 10 to the minus 3 kilograms per mole. And then we're going to divide that by 3 times 8.314 joules per mole per Kelvin. And so this is going to give us our answer in units of Kelvin. So I'm getting 52.5 degrees Kelvin. And that makes sense because hydrogen molecules are smaller than nitrogen molecules, okay? And so if we compare this graph here, right, we need to figure out at what, basically in order to get xenon, okay, to have the same average speed as helium at a particular temperature, you're going to need to heat the xenon up in order to shift its distribution to be coincidental with that of helium. The same thing's true in this problem here. Nitrogen is heavier than hydrogen, and so in order to get the average speed of hydrogen to be the same as nitrogen at 455 degrees Celsius, you're going to have to cool that hydrogen down relative to the nitrogen so that they have the same speeds. And so you're going to have to get it down to 52.5 degrees Celsius. In this problem, this is not really a problem. They just want us to show something. They want you to use the fact that, the root mean square speed, which is 3RT over M, square root of that. They want you to show that this can be used to derive Graham's law. Well, if the rate of effusion of a particular gas, we'll just call it gas 1, is proportional to the root mean square speed at a fixed temperature, that means it's proportional to the square root of 1 over the molar mass. Well, that's Graham's law. And so if you take the same thing for a second gas, rate 2, proportional to the root mean square speed of the second one, you get the square root of 1 over m2. And then if you take the ratio of the two, you're going to get the square root of m2 over m1, which was Graham's law, which we used in the previous video. Before I stop the video, I realized that I forgot to do this follow-up, and that's an important one. So let me go back to that problem. Okay. So the two gas molecules, at what, the two different gases, to have the same average speed, they would need to have different temperatures. What about the follow-up question? At what temperature do the gas molecules have the same kinetic energy? This is actually a trick question because the average kinetic energy is equal to 3/2 RT. It only depends on temperature. And so if the two gas molecules have the same temperature, then they have the same average kinetic energy. Okay, so it's a trick question. At what temperature do hydrogen molecules have the same average kinetic energy as nitrogen molecules? The answer is 455 degrees Celsius. With that, I will go ahead and stop this video, and we'll pick up with the real gases in the next one.